here is the copula-based mixture mole. Its density, let's call it H, of x1 up to xd. D is the dimension. So its density H writes as a sum over Z equals to 1 to K. K is the number of clusters of CZ. CZ is the copula density in the Z group of H1Z, capital H. It's the cumulative distribution function of the first variable in the Z group up to HDZ of xd times the product of the conditional margins, the product over J equals to 1 from to D of H J Z X J times pi Z. Pi Z is the probability for an observation to belong to the Z cluster, and H A H J Z small h is the density associated to capital H J Z. Alright, so there is bracket here and here. This is the copula based mixture model. Now, what are the limitations of this model? Suppose you want to build a parametric model out of this equation. What you have to do is to make choices for the parametric families. There are choices for the CZ, there are K choices, and there are choices for the H, J, Z. There are D times K choices, which in total gives K plus D K choices to make. So admittedly, this is not very convenient for the practitioner of statistics. So in my paper, Semiparametric and Location Shift Copula-based Mixture Model, I tried to overcome these limitations by assuming the following hypothesis. Assume that H, J, Z of X writes as G, J of X minus mu J, Z for each J and each Z. Mu J, Z is the mean of the J's variable in the Z's group, or the Z's cluster, and Gj is a symmetric density. So what does this mean is that, so let's draw a picture. So here I have 0. Let's say here I have mu J1, and here I have mu J2. So mu J2 is the mean of the J's variable in the second group, and mu J1 is the mean of the J's variable in the first group. And suppose that here I have Gj, so it's a symmetric density, so it's something like this. Now, what this equation means is that if I want to obtain Hj1, I need to shift Gj here so that it is centered around mu j1. So perhaps I have something like this. And exactly the same applies for Hj2. So I have, I don't know, something like this. All these densities are identical up to a shift here. Okay, now let's see what happens in 2 dimensions. In 2 dimensions now, let's draw a picture. So let's draw the first variable around here, j equals to 1, and the second variable around here, j equals to 2. And suppose my first group is around here, something like this, maybe z equals to 1, and my second group is somewhere here. Yeah, z equals to 2. All right. Now, how looks H11? Well, something like this, right? This is H11. And how looks H12? Well, something like this as well, right? This is H12. And we can see that these 2 densities are identical up to shift. And exactly the same applies for the second variable. We have H21 here and H22 here. And again, these densities are identical up to shift. Now, this is a situation which is permitted by our model. All right. Now, suppose that I have more points on the right of my second group. Perhaps something like this. Well, H12 no longer has this shape, but it looks more like my software is freezing. No, okay. Yeah, so the density probably looks more like it's more high here, perhaps more something like this. And we see that this is no longer true. H12 and H11 are no longer identical up to shift. So this situation here is not allowed by our model. What is allowed, however, is the following situation. So now, I remove some of the point I created, and we're going to assume that the groups are more stretched from north to south. So we have some point here. and here as well. Well, I erase H12. Okay. And I redraw. So something like this. All right. Now, in the first variable, for j equals to 1, the densities didn't change, but for j equals to 2, for the second variable, the densities did change because the points are far more stretched. So we probably have densities with a heavier tails, probably something like this, right? Something like this. Well, so this is a situation we can have in our model because in both variables we still have the location shift hypothesis, even though here, if we consider J1, it is obvious that it is not equal to J2 because here J1 is probably more like a Gaussian, while G2 may be more like of a student distribution in the sense that the tail is heavy, but the Gaussian, the tail is light. Okay. Oh, sorry for this. So the location shift copula based model writes like this: hx1 at 2xd writes there is still this sum from z equals to 1 up to k of cz, and here in the argument I put g1 of x1 minus nu1 z, where g1 is the cumulative distribution function corresponding to the density small g1. So I do the same with gd, xd minus mu dz, times the product of the margin distribution, the conditional margin distributions, but remember that they write gj xj minus mu jd times pi z. I put the bracket here, one here. All right, so this is the location shift copula based mixture model. Now, what is cool in this model is that look at the parameters. Well, let's suppose that parametric family has been chosen for the copula, so that there is theta z here, the copula parameter. Look at our model. We no longer have choices to make. The only thing we assume about Gj is that it is a symmetric density. That's it. And yet, it turns out that we can perform estimation in this very model. It turns out that we can estimate Gj non-parametrically. so that our model can adapt to the data with no modeling efforts. And that's the cool stuff about it. Now, if you want more details, you can see my paper. It is available on my website, and that's it. Thank you very much.